Hello and welcome. In this video, we're going to talk about a very important topic in data science, which is known as bias and variance trade-off. It is seen that in most of the interviews, there would be questions related to bias-variance trade-off. Hence, it becomes very important for you to understand it the right way. Now, if you follow our channel, you'd know that we typically cover a topic to a decent depth. If you're new here, please consider subscribing to this channel and don't forget to share it with all those who might benefit. Let's get started. Before we get into the bias and variance concept, let's understand in general a few things about data. So when we have data, it has two broad components. First is information. Second is noise. Information is the useful part of the data that we are interested in and we want to capture with the help of our models. Noise, on the other hand, is the random, unpredictable, and irrelevant part of the data, which is not very useful information. So it is considered undesirable. So what is a good model? A model which captures the information from the data and leaves aside the noise is a good model. Whereas if a model begins to capture noise along with the information, would not be considered that good. Let's understand another general concept. Whenever we study, in the process, we learn something. We're getting trained on something. And what really confirms that we have studied well, typically it will be through a test. So if we have studied well, we've been trained well, and if we do well in the test, then we are ready to graduate or qualify. But if for some reason we do not do that well in the test, then we disqualify and we have to study again. Now, this is something that holds good for machines as well. So when we get any data, we don't use this entire data for machine learning. We always divide the data into two parts. A larger part, which is called train, which is equivalent to the kind of study or preparation we do ourselves as practice. And the smaller portion of the data, which is called test, is used for evaluating the model. A model is considered good when it does well on both training and test. If a model is doing excellent on train set, but does not do that well on test, it is not a good model. It is like when one studies and gets very good scores in training during the mock tests, but when the actual assessment happens, this person doesn't do that well. So remember, when you're given a data, you would not use the entire data for machine learning. You will only use a portion of it. Typically, 70% is allocated to training and 30% is parked for test. But this can vary depending on the size of the data as well. Important thing is, a model is good if it is able to perform well in the test set and it's consistent with its trained performance. This much background was needed to be able to understand the bias and variance concepts. We'll get these references as we proceed. Let's understand the bias error. Let's say these are the two instances of our data. Our data is like this. Now let's say we try to fit models to these data sets. First option is on the left, you get a straight line which is trying to represent these points. And on the right, you have another model which is trying to again represent these points. It's a little more complex model. Which is a good model? Well, I guess your answer would be that the model on the left seems to be not doing that well. If this line is supposed to represent these points, then probably it's not doing a good job. On the other hand, this complex model that you see seems to be doing it too well, kind of a too good to be true scenario. Let's understand this with the help of error. So what is an error? This is your model. This dotted line, this black line represents your model, and these red lines here represent the distance from the actual points. So these are our error terms. Obviously, we are making a lot of errors here. For this point, which is on the line, maybe the error is negligible. But for the other points, we are making a lot of error. And this is a scenario which is called a high bias error. In other words, we also call it an underfit. On the other hand, the visualization on the right, if you see, seems to be doing it too well. So you, of course, have a low bias error. In fact, a zero bias error in this case, we can say. Is that a problem? At least not so far. In general, how do we define a bias error? Bias error happens when a model is so simple that it fails to capture the true relationships present in the data. So when you're not able to capture how the independent variables or X variables explain the Y variables or the outcomes, then you're committing a high bias error as we fit a model to the training data. Let's deep dive a little further onto this low bias error piece. Do we have a problem with this as well? Let's understand this. So let's say we now got new observations. Remember, any model that you prepare is typically prepared on the historical data. But where is it going to be useful? It's going to get used for future data. Because you depended too well on the historical data, you may be making many errors when new data shows up. So is this good? Of course not, because end objective is to do better on the test data. Are we making errors? Of course, yes. And this is called a variance error. So in this case, we don't have bias, but we have a high variance error because all these new points that we got are not fitting the model as good as it was the case with the training data. And this, to be precise, is called an overfit. So once again, what was an underfit? When to begin with, in training itself, you're not able to fit an appropriate model. That's called an underfit. What is an overfit? When you're fitting too well in the training set, but on the test data, you do not perform that well. So let's understand what is a variance error. A variance error arises when a model is too sensitive to even small fluctuations in the data. When there are slight changes in the kind of data that you've seen and the data that you get, your model is failing miserably. Just to remind you of the same example, maybe in the mock test or studying at home, the student was doing quite well. But when the real test happened and it was again very time bound, the student didn't do that well. So as a result, the student has to study it all over again. An interesting example related to overfitting that I would want to mention here is related to computer vision. So data today is not just limited to the spreadsheets or SQL format. The data could be images as well as audio and text. In computer vision, it is a very common task to identify the object, differentiate the objects, let's say cats versus dogs. Similarly, an exercise was conducted where they were trying to differentiate between the huskies, the domestic ones, versus the wolves, which are the wild creatures. This is the image of a husky, which you can see is probably in a domestic setup. You can see a garden and the husky is there probably playing with a ball. And on the right, you see an image of a wolf, which is with a certain background. And there are similarities, but a computer vision model would be doing well if it is able to clearly call out when it's a husky versus when it is a wolf. So some of the models did quite well. But later on, to the surprise, it was figured out that the model was not able to actually differentiate between a husky and a wolf. The model was actually using the background to understand the difference between the husky and the wolf. So most of the images of the wolf fed to the model had snow in the background. Model did not look at the features involved with the husky, like the size compared to a wolf or the tail and the other aspects. Model only considered the background. Husky was typically seen in a domestic background, a house-like background, an internal or external setup, but relative to where people live, whereas the wolf was seen in more wild setups, primarily with snow in the background. So what caused people to figure out that this was the actual problem? When they exposed the model to the images of a husky with a snowy background, they figured out that the model declared it to be a wolf because the model did not concentrate on the object itself, but the background. What is this? This is a clear example of overfitting. Relying on the kind of features which are not relevant is overfitting. Capturing the noise to explain an outcome is overfitting. So what could be a solution? Let's understand that. For the same data, we've discussed the bias and variance. Let's say we get a different model, a model like this. Now, if you see, this is not perfectly fitting these points. There is some gap here at places. So what would happen now is you can calculate the error. It's not a perfect fit. There is some error. But what that ensures is when you get new observations, the difference between train and test performance would not be that significant. So you will make some errors with respect to the test, but you also made some errors with respect to train. So what is happening now? We are making some test errors, which we were making earlier as well with a different model. And you can see those errors overall have reduced because of a more generalizable model that you've chosen. So now you're being more practical. You're making some errors during the training and you're making some errors during the test. And this makes the model a low bias and low variance error. Notice this is a low bias error, not as low as 0, which was the case here, which was an extreme case. We still have low bias error and we also have a low variance error. Why is the variance low? Because the train and test errors are now comparable. And this is like the example where whatever you did in your tests at home or the mock tests at home, you're able to replicate the same in the actual test. And as a result, of course, you end up graduating. So any discussion related to bias and variance would be incomplete without this image. What does it explain? It explains model complexity and the error, complexity on the x-axis and error on the y-axis. You can see this red line represents bias. So what happens is, as you continue to make the model more and more complex, the bias error continues to reduce. On the other hand, at the same time, the variance continues to go up as the model gets more and more complex. Why? Because a complex model means it's putting all the hard effort to ensure that it's able to fit every tiny bit of the training data, which later on becomes a problem because it is not generalizable. So you can see, if we do a total of these two errors, this is the black curve that you would get. So why do we call it a trade-off, and where does the trade-off happen? It's called a trade-off because we settle for a point where the total error is minimum. So we don't want to keep the model too simple, such that it has a high bias error but low variance. On the other hand, we don't want the model to be too complex that it has a low bias and high variance. That's why we call it a trade-off. What's the ideal point? Where the total error is minimum would be the right amount of complexity for the model. Not too simple, not too complex. Now let's quickly understand the causes and cures of bias and variance errors, a very important interview question. So a bias error happens because the models are very simple. We saw in our example, we had a straight line explaining a relatively complex pattern. And the second reason for bias error is when we have insufficient relevant features. Probably because of the lack of the subject matter knowledge, we may have not even collected enough features to be able to explain an outcome. So for example, you're trying to predict somebody's pay. Pay could be a function of a number of factors. For example, the job role, the experience, the qualification, the performance in the organization, and many more factors. But let's say you only rely on the experience. You don't look at the qualification, you don't look at the other features. Would you be able to predict the salary properly? Answer is no. Probably you did not consider enough features while creating your model, and that causes a bias error. On the other hand, what are the factors that lead to variance error? Complex models. Remember, we neither want too simple a model nor too complex a model. We have to settle for something in between. Second could be that we're using noisy or redundant features. Just like in the Huskies versus Wolves example, you saw snow as a feature being used to decide which animal it is. And what also leads to variance error is the insufficient training data. You saw very limited examples, so you will not be able to differentiate very well. It's like you study a topic and you find it pretty complex, but you've not practiced it enough. If you practice it enough, that complex would have become simple for you. But if you did not practice enough, you did not train yourself on enough problems, then it's an insufficient training issue. And lastly, it could also be a data leakage issue. A very interesting problem. Let me just elaborate this. I'll take you to a common problem which is related to predicting whether a patient is diabetic or not. There are many versions of such data sets which are available online. And in almost all the solutions, we find out a very important feature people are using to predict diabetes is change of medication. Now, this is fundamentally wrong. Why? Because change of medication actually happens when diabetes is detected and not the other way. So this is called data leakage. You brought in a feature which is helping you cheat while predicting the target. Coming back to the cures. So if we are using too simplistic models in case of bias error, we can try more complex models. We can try different models. If we have insufficient relevant features, we can add more features, asking the subject matter experts, or doing something known as the feature engineering. Likewise, for complex models, we can try regularization or hyperparameter tuning. For noisy and redundant features, we can perform feature elimination. For insufficient training data, it's obvious we can try to increase the training data. All right, so this kind of sums up everything that we wanted to discuss about the bias and variance error. Hope it helps. And if it does, do consider sharing with all those who might benefit. Thank you.